Okay, Assalamualaikum and good morning, everyone.
Waalaikumsalam.
Okay, today we are going to continue with the Hurwitz method. So on Monday, we have learned about Hurwitz method for normal cases. And today we are going to look at what happens if you have, if you encounter special cases when generating the table using Hurwitz criteria, okay, or Hurwitz method. So Hurwitz method needs modification when you encountered with the following special cases. Okay, so the first case is when you encounter a, a zero value in the first column of the table. And the second one is when you encounter zero values in an entire row of the table. Okay, so there are two special cases. So let's look at the first case. Okay, so case one is when you encounter zero in the first column. So let's say you are given this transfer function, closed loop transfer function, and then you can generate the table from the denominator. So you start with s power 5. The two top rows with coefficients of the denominator alternatingly. And then you can calculate row S3. So when you calculate row S3, you will encounter zero here. Okay, so here there's a zero. So what happens is that when you calculate the determinant, so you get zero. Okay, so when you encounter zero in the first column, and then you calculate the next column, you get 7/2, and then zero. Okay, so when you encounter the first zero, what you need to do is, okay, later let's look at this first. Okay, so how many poles are there in this denominator? Okay, so you have s power of 5, meaning that you have 5 poles, okay, or 5 values of s when the denominator equals 0. Okay, so meaning that you have 5 poles. So we need to determine how many poles on the left or on the right half plane of the S plane. So here, when you encounter 0 in the first column of row S3, what you need to do is you need to modify this value 0 by replacing it with a small number. So we represent the small number using this symbol epsilon. Okay, when you assume 0 equals a small number epsilon, then you can continue calculating the value of the next row. So if you have, if you use the value 0 here, what happens is that the next row here will become something over 0, which is impossible to calculate, okay, when you divide something with 0. So that's why we replace the value 0 with a small number. We use the symbol epsilon. Then when you apply the value epsilon here, then you can continue calculating as usual. Then after that, we need to determine how many poles or how many sign changes in the first column. So what we need to do is we assume that the small value epsilon here can either be positive or or negative. Okay, so a small positive value or small negative values. So here, if we assume epsilon as a small positive value, then we can determine whether the column has sign changes or not. Okay, so the first value here, row S5 is positive, S4 positive, so S3, we assume epsilon a small positive value, so it's a positive. Then row S2, if we assume epsilon a small positive value, so let's say we assume epsilon equals 0.1, for example, 0.1. So you can calculate, so 6 times 0.1 minus 7 divided by 0.1. So you get about negative 64. Okay, so if we assume epsilon 0.1, so it's a negative number, so you get negative here. Then you do the same thing for row S1. You assume epsilon a small positive number, let's say 0.1, then you calculate, and you get positive. And then row S0 is already positive. So here there are two sign changes, one here and then one here. And then we repeat the process, assuming epsilon as a negative number. Okay, so a small negative number, let's say negative 0.1. So you repeat the process. So row S3 become negative, S2 becomes positive, and row S1 positive as well. So here we have two sign changes. Okay, there are two sign changes. So there are two poles located on the right-hand side of S-plane. So the system is unstable. Okay. But it's a bit tedious to use this epsilon symbol and then assume it's positive, negative, and so on. So there is another alternative way we can do to avoid using epsilon. So to do this, we need to reverse the coefficient of the transfer function. So after you determine you have 0 in the first column, after you find 0 in the first column, then we know that we need to perform some modification. So instead of applying symbol epsilon, we reverse the coefficient. So how to reverse it? So this is the original denominator. So you just reverse the coefficient, okay? So we start with 3. So from 3s0 becomes 3s power of 5. And then 5s power of 4, 6s power of 3, 3 becomes 3s power of 2, 2 becomes 2 times s, and then 1 here becomes 1, okay? 1 s power of 5 becomes 1. So you just reverse the coefficient. And then after that, we repeat the process of generating the Routh table. So we use the new transfer function or the new denominator that we have reversed. Then we generate a new Hurwitz table. Okay, so here we get two sign changes here, one here and one here. So similar answer as previous method by assuming a small epsilon value. Okay. Okay. Any questions so far? So please be reminded that to use the reverse coefficient method, you need to show that there's a 0 in the first column. Okay, when there's a 0 in the first column, then only you can reverse the coefficient. So from previous semesters, what usually students did was they reverse the coefficient without showing that there's a 0 in the first column. Okay, because maybe the question already indicate, like the question says the transfer function um, has 0 in the first column, so student didn't show, maybe something like that. But the appropriate way to do this is to show first that there's a 0 in the first column, then you can reverse the coefficient. Okay. So I think this is quite straightforward. Now let's look at second case, when you encounter 0 in an entire row. So let's say you are given this transfer function here, and then you generate the Routh table. So we start with s power of 5, followed by s power of 4, and then we fill the two top rows with the coefficient of the denominator alternatingly. Okay, so we fill, and then here we start with 7, 42, and 56. We can factorize the number, but you can also choose to not factorize. It will produce the same result. Okay. And then after that, we calculate the row S3. So we encounter 0 in an entire row. So here, all rows, the values for row S3 are 0. Okay. So what we need to do is we need to go back to the previous row, which is row S4. Go back to row S4, and then create a polynomial. So a polynomial PS is created from row S4 by taking the first value here, 1, 1 S4, 1 times S power of 4, plus 6 times S power of 2, plus 8 times S power of 0. Okay, so you reduce the power by 2. Okay, so we start with S power of 4, and then S power of 2, and then S power of 0. So let's say if this is S6, row S6, so you start with 1 times S power of 6 plus 6 times S power of 4 plus 8 times S power of 2, and so on. So you reduce by 2 power. And then after that, we differentiate this polynomial with respect to S. So we get 4 times S cubed plus 12S. And then we use this differentiated form to replace the row S3. So we use 4, we put in the first column, and then 12 in the second column. And then we don't have any more coefficient, so we just put 0 in the remaining column. Then after we put the value 4, 12, and 0, so here you can simplify by factorizing 4, or you can choose not to simplify. Then we calculate row S2 and so on as usual. Okay, continue as usual. So you get the remaining rows. So from here, we don't have any sign changes. So the system is stable. No sign changes in the first column.
No sign changes. Kat mana dah tu?
Ni
Gate
first
0.
column. Dekat kolom pertama. Okay, let's look at another example. So let's say you are given this polynomial, and then we generate the Routh table. And then here we encounter 0 in the row S3. So what we need to do is we look at row S4 and generate a new polynomial PS. So 1 S power of 4 plus 3 S power of 2 plus 2. Okay. and then differentiate. Then we use this differentiated form and replace the original row S3. Then we calculate as usual. So here is the new row S3, 4, 6, and 0. And you can choose to simplify. So the example further simplify the calculation. And obtain the remaining rows. So here, if you encounter 0 in a row, so here the first part here from S power of 8 until S power of 4, there are two sign changes here, from S7 to S6 and from S6 to S5. So meaning that from row S8 until S4, there are two sign changes and two poles located on right hand side of S-plane. And then the remaining rows from S4 until S0 or S0, there are no sign changes. So usually this is because after you encounter 0, then there will be no sign changes after the row, the zeros, the zeros row. So this is because of symmetry of the later on we will see in a topic after midterm, symmetry of the S-plane. Okay, so what I mean by that is that let's say if you encounter value of S as a complex number. So when you encounter a complex number of S equals, let's say, A plus B times J. So there must be another complex number, but with negative Bj. Okay. This is if you still remember your maths back in first year, this is called a complex conjugate. Okay. So a complex number, dia ada conjugate dia ada conjugate lah. So maksudnya if one is positive, the other one is negative. So this is called complex conjugate. So later on we will see this complex conjugate and how it actually helps in this symmetrical, okay, symmetrical of the S-plane. Okay. And that's it. Any question before we end this lecture?
Tak faham lagi doktor, tapi cuba buat lah.
Okay, tak apa. Later on masa cuti ke ada masa boleh try tutorial. Okay. So that's it for Hurwitz criteria, and we will discuss the tutorial after Hari Raya, and don't forget to submit your project part 2 tonight and your quiz number 3 Friday. Okay. And I think that's it. If you don't have any question, that's it. Then I want to wish Selamat Hari Raya to all Muslim, and for non-Muslim, happy holiday. Hope you have stress-free holiday without assignments. Okay. So see you again after midterm break, insyaAllah. Assalamualaikum and goodbye.
Waalaikumsalam doktor. Selamat hari raya.
Thank you.
Thank you, Doctor.
Thank you.
Salam, thank you Dr.